think you already know what it is. We just haven't formally called it that. The first derivative test is used to determine where max and min are, and then from there to determine what they are. So if we assume that a function is continuous at c, so at x equals c, which is just some location horizontally, if I say it's continuous at c, that means someplace to the left of c there's a point, and someplace to the right of c there's a point where I can connect those points without lifting my pencil as I pass through c. It means literally what you suspect it means, that there's no breaks at c. From c, you can go to the left and to the right. And x equals c is a critical number. If that's the case, and this you already know, it's just the way calculus is taught. If the first derivative changes from being positive to negative as we pass through c, then there must be a maximum at c. And the reason for that is really simple. If you have, I'm just drawing a number line here, and I'm going to label that as x, and this is the critical value of x. If I told you that the first derivative, and I apologize for very often saying the first derivative, because I can just say derivative, but later we'll talk about the second derivative. Okay? If I say the first derivative is positive and then it's negative, it implies something about the first derivative at c. It implies that the first derivative is not positive at c and not negative at c. It's either 0 or undefined. Then what that tells you is that the function is increasing and then decreasing. So the line, the straight black line is x. The green arrows represent what the function is doing. The only way you can go from having a positive to a negative slope is if you change direction and you go downwards. So that's a maximum. Similarly, and I don't think I need to draw that again, well, I guess I will. If you had the same situation where you had dy dx that's negative, and then all of a sudden at some point it changes positive, then what that means is the function is decreasing because it has a negative slope and then increasing, which means there's a minimum. It's just a way to visualize it. But I think you already knew that. In fact, one of the examples we finished off with yesterday, we had those arrows at the end, and we said, well, if it goes up and then down, it's a max. We have two examples we're going to go through. But basically, just to give you a visual of this, if you make a first derivative chart and it happens to be that your first derivative takes on those characteristics, then that means in that first interval, the function is increasing. It's increasing in the second interval, then decreasing, increasing, and decreasing. So what that means is right there is where there's a maximum. Where that second interval ends and the third interval begins would be a maximum. And this would be a minimum, and that would be a maximum. So we're formalizing what we did over the past couple of days. Find all maxima and minima for the following functions. These are open functions. There are no restrictions in terms of the domain unless there are non-permissible values. Like, we still can't just say, well, because they're open, I could take the square root of a negative number. Can't do that. You still can't say, just because they're open doesn't mean I'm allowed to divide by 0. There's still restrictions. So in this case, though, it's polynomial. We can make a mental note that x here is an element of all real numbers. What that means is this is truly defined everywhere. The derivative is quite simple to find. I'm going to use the dy dx notation here. It's 15x to the 4 minus 15x squared. And we want to do all of our factoring now to decide what the critical values of x are. Good luck. So we're going to factor this. I can see I can factor a 15x squared out. and have left x squared minus 1. Fair enough? The x squared minus 1 is a difference of perfect squares, so I can write this as dy dx equals 15x squared times x plus 1 times x minus 1. And again, you don't need to write equals 0 and do a bunch of algebra. You should be able to look at that and tell me that the critical values of x are going to be -1, 0, and 1. Plus or minus 1 for the two binomial factors, or plus or minus 1 for the x squared minus 1, if you like, and 0 for the factor of 15x squared. Since this function was defined everywhere, that means our subdomains need to cover everything from negative infinity to infinity. So we start at negative infinity. We go to the critical number of -1. Then we go from that critical value of x to the next. We go from that critical value to the next. And then we go from the final critical value to positive infinity. And we put up all of our factors at the top. I'm a little curious here. How many of you would put, instead of x plus 1, x minus 1, x squared minus 1? Anybody? You might? I can see some of you kind of going, I can see that. I'm going to erase this. I'll bring it back in a second. My comment to you is if you do this, that's fine, but you need to understand it's going to switch twice because it's quadratic. It's going to go from positive to negative someplace and back to positive. And the comment I would make to you is if you're going to do that, you're just one tweak away from just having one column and just doing the whole derivative. You know, and really you could, I suppose. The purpose of having all of the factors separated is to make your work easier to follow and harder to make a mistake. Whoops. So 15x squared is positive everywhere because you're squaring x. It doesn't matter what value of x you put in, you're going to get a positive number. The other day somebody asked, and many of you might ask as well in your head, well, can't you get 0? And the answer is no, you cannot get 0 because 0 is a critical value. And 0 is right here, which is not in an interval. Okay? None of those intervals include 0. 0 is between intervals. It's the boundary of them. And then this will be negative, then positive, positive, positive. Make sure you agree with me. And then negative, 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 positive. I'm going to just add something to this. I don't think you want to add it, but had you put the x squared minus 1, you would have had positive here, because this together will be positive. You would have had negative here, and positive there. Just if you want to go that path. So now we can write out what dy dx is in terms of positive or negative. I always just circle this so that you don't confuse what I'm writing in this column with the other stuff. You should be all getting pretty well versed at drawing or completing these charts. Yeah? What I would say? Okay, good. What does that tell us about the function? It tells us the function is increasing, then decreasing, then decreasing, then increasing. Again, very basic example. What does that tell us? It tells us that there is a maximum here. And look how where I wrote that word max. It's not in the interval above, and it's not in the second interval. It's the boundary between them. And then we also have a minimum here. So in terms of coordinates, we have a max. We have a maximum that was at x equals -1, and a minimum at +1, all you have to do now is find the coordinates of the points, the y coordinate. So we go back up to the original function, which was 3x to the 5 minus 5x to the 3. You put positive 1 in, and you get negative 2. I'm thinking. You put negative 1 in, and you get positive 2. There's a reason why, by the way, the y coordinates are opposite, and it has something to do with the fact that this function is odd. I don't mean odd just degree 5. It's perfectly odd. Everything on this side of the origin that's going down mirrors everything on this side that's going up. It's not just odd because the arms are in opposite directions. Let me demonstrate that to you. If I were to graph 3x raised to the 5 minus 5x raised to the 3, once again, is that correct? Okay. And I set up my window settings so that I can see details of these important features. So I'm going to go from negative 2 to 2, up by 1, and it's going to climb a bit more. So I'm going to go from negative 10 to 10, up by 1 for y. It's a perfect 180-degree flip around the origin. And we'll learn about that in Chapter 5. That's called an odd function. Not just odd because it's degree 5. It's a perfect symmetry. It's like this. By the way, if I were to go trace negative 1, trace negative 1, well, there's my maximum. You could go into your calculate menu and find the maximum that way as well, just to confirm it. And if I go trace 1, there's my minimum. Any questions with that example? Yes?
How can you have a critical point that isn't a max or a min?
It's a good question. The question is, how can a point be critical if it's not a max or a min? In this specific case. And the reason why I think you're asking is, it isn't that it's critical because there's something undefined. That's easier to swallow. Oh, if the derivative's undefined, I can see why it's not a max-min. Although, and I'm going to get back to your question, it's weird to try to figure out how, if the derivative is undefined, you do get a maximum or a minimum. And we'll have to talk more about that later. The answer to your question is it's an inflection point that bottoms out with a slope of 0. Okay, so let me... my graphing calculator can probably do a better job than I can. I'm going to just shave off part of this. Let's go negative 4 to 4. And I'm going to turn off the axes. And before I graph it, would you agree if I took the original function, and you can look on your handout for this, and I factor out x cubed? That's what it is? Okay. So what this means, and I'm reaching back into Math 30-1, is that there is an x-intercept of 0 because of that factor of 0, but it is a multiplicity of 3. And by the way, we don't often encounter this in Math 30, although it's legitimate. There's a quadratic that's not factorable, but there are values of x that make that 0, plus or minus the square root of 5/3. So there are two other x-intercepts, each with a multiplicity of 1, combining to give a quadratic with a multiplicity of 1. Okay. However, when we draw inflection points, and you're asking a really important question. When we draw inflection points in Math 30, and we say there's an inflection point at 0, we tend to just say, it looks like that. And I will even tell my Math 30 students, I don't know if you remember this, we don't know the severity of the inflection point. You remember that this is an inflection point, right? We don't know the severity of it. It might look like that. It might look like this. It might look like this. I mean, there's all kinds of scenarios. But since the derivative was 0 here, it was a critical value because the derivative is 0. That means the slope at that point is, in fact, 0. So it's inflecting, and it's getting a slope of 0 at that instant when it passes through the origin. And that's what I'm going to show you here. And it looks, I know it looks like there's a whole region there with a slope of 0. But that's a defect in your calculator's ability to graph details. There is a point right here where the slope of the tangent is exactly 0. If you were to go a little bit, just any amount to the left, the slope would be some very tiny negative number. And any amount to the right, it would be some tiny positive number. So how that happens is there's an inflection point. There are other ways it could happen. Have I answered your question? Okay. Any other questions with that example? By the way, chapter 5 is all about graphing, so we're going to end up pooling all of these ideas together eventually. Let's try one last one. This function, and we will learn about this in chapter 5, is not odd, it's even. It's not even a polynomial function, it's even. And I'll tell you why you know it's even. Why I know it's even. Let me go back to this one. How many of you understand why in this one? Why the y coordinates ended up being opposite by looking at the function? That when you put -1 in for x, you happen to get a positive number, but when you put +1 in, you get the same number, but it's negative. It's because both of those exponents are odd, and when you put negatives in, they flip the signs. Or they keep the sign the same, but if you put a positive in, you get a positive result. Okay. What happens when you put, say, +1 in for x here, and then you put -1 in for x? Do you get a different result? You get the same result. Which means if my nose is the origin, whatever the graph looks like over here, it has to look like it over here. It's not this way. It's this way or this way. So let's find the derivative. First of all, f of x is 1 plus x squared to the -1. I think this is the quickest path to take rather than using the quotient rule. So f prime of x is -1, 1 plus x squared to the -2 times 2x. Can we all buy that? Okay. Okay, so that means the derivative is -2x over 1 plus x squared. There is exactly one critical value of x for this derivative. The function's defined everywhere, so there's not a critical value of x at the beginning or the end, okay, where derivatives are not defined. It's impossible when I eyeball the bottom of this, it's impossible for me to make that 0. I can't, because it's 1 plus something squared. The only way that could be equal to 0 is if you solved this equation, which would give you x squared equals -1, and now we're in the realm of imaginary numbers. Yeah?
Should 1 plus x squared all be squared?
Oh, is it? Yes, it is. Thank you. So, and let's talk about that. You're right. The bottom cannot be 0, and it's not because the whole bottom is squared, though. The bottom cannot be 0 because 1 plus x squared is going to be positive, which in turn makes 1 plus x squared positive. Yes, I forgot my squared there. So there's no critical values of x there. I hope you can see that when you look at the top, you have a critical value of x of 0. So the derivative is going to be very straightforward in terms of putting it into a table. We are going to go from negative infinity to 0 and from 0 to infinity. By the way, whenever you have any kind of symmetry, the last one was odd, remember that? All of your domains in your chart will be mirrored on the other side of 0. There will be some symmetry to the cutting of the entire domain. If we go back and look at this, these domains are symmetrical to each other, right? Similarly, if this is an even function, the domains are mirrors of each other. There's symmetry. Okay, so across the top we have negative 2x, and we have 1 plus x squared, quantity squared, which, by the way, is positive everywhere. It turns out that this is kind of a boring graph. There's not much to it once you see it. Give a little bit of thought to the idea that the negative 2x goes from being positive to negative. Okay? That means the derivative is positive and then negative. That means the function is increasing, then decreasing, which means that what we have right here is a maximum, and the maximum will have coordinates of 0, comma, whatever f of 0 is. So we go back up to the original function, put 0 in for x. Shouldn't really require much thought to see you get 1. Was it 1 over 1 plus x squared? 1 plus x squared when x is 0 is 1. 1 over 1 is 1. So there's a maximum there. I can tell you right now what this graph is going to look like. Now I'm thinking this out in another way too. It's going to look like this. I'm working out the details of it by looking at other features of the function. I'm looking at the fact that the x-axis is a horizontal asymptote because the degree on the top is smaller than the degree on the bottom. We'll deal with that in chapter 5. If we take a look at it here, and by the way, the y-intercept is 1 because that's where the maximum is. Is it 1 over 1 plus x squared? I'll go from negative 4 to 4, and I will go from negative 1. No. I'll go from 0 to 1.5. So I can turn my axes back on. So that's what it looks like. Not much to it. Just to let you know where we're going in terms of other things in this unit. Do you all see that in this region right here, generally speaking, the graph has that kind of curving to it? But in this region, it definitely has that kind of curving to it. And in this region, it has that kind of curving. It has to change from curving this way, from curving like a bowl that would catch water in the rain, into an umbrella. It's got to change somewhere. There's got to be a point where it does that. That's an inflection point. It's just not on the axis. And the location of the inflection point is probably ish. The second derivative is what you would use to find those positions. There's a relationship here between the second derivative and the graph. Anyway, that's a couple of weeks away. In the meantime, you have some questions to practice here which deal with basically the first derivative test, which is to use your derivative in a table to find max mins and then find coordinates. You also have those 2 written response. You can certainly use class time to work on those. It's up to you at this level what it is you want to work on. And if you want to check out the U of A site for that, absolutely. Probably more valuable than giraffes and shadows. By the way, just to show this to you, from years past, well, this was last year, I'm expecting some good diagrams here. It's the giraffe. This was last year. That we're getting there. Still a little childlike. Infant-like, maybe. I'm just teasing, by the way, if you want to draw your giraffe that way. I don't, that one, I like this one, because you look closer and closer and closer, and I don't know what it is. It's an alien giraffe. And then, that's interesting. Another basic one, just in case I wasn't sure that, the person said there's the giraffe. Ooh, look at that. That's pretty snazzy. And a happy giraffe. It's almost like a pony, I think. Or a cow has mated with a giraffe.